So moving on, let's build up the p orbitals. Okay. So there's a lot of stuff going on here. I realize it looks pretty intimidating. So let's put it together piece at a time. So remember, we've got psi2, 1, 0. So n is equal to 2. L is equal to 1. And now specifically, we're going to look at ML equals 0. And I'll remind you that ML equals 0 is special for the z-axis. So by definition, when we look at psi2, 1, 0, we're looking specifically at PZ. And we're going to create this PZ wave function, psi PZ, and specifically we'll define our p orbital as the square modulus psi star psi of psi210. Okay, so let's build that up. So I can separate that into the radial and angular components, r21 and y10. Okay, and so instead of saying 210, we'll just adopt the psi pz nomenclature. And now if we look at our spherical harmonic function and our radial function, then we're just going to smash them together. Literally multiply, the root of 3 over 4 pi cosine theta times this radial function. Okay. And so there's some algebra that's been done. And so I'll also remind you, right, that rho is this 2zr over na. So I'm not going to worry too much about going through the algebra, showing you where this comes from. But basically, it's this function times this function, right? That's how we got it, okay? And then collected like terms. So what's also pretty cool, what I'm going to remind you, the reason why we really like to adopt this PZ nomenclature, not only because ML equals 0 is special to the z-axis, but also if you recall, that when we do a Cartesian coordinate transformation, z equals r cosine of theta. So that was one of our coordinate transformations from Cartesian to spherical polar chords. Okay, so this was done algebraically. So there was an algebraic manipulation here to show you that here is this r cosine theta, which I'll highlight, and then there it is right there, and then that just becomes z. And then all of this other stuff that I'll box off in red, or here I'll bubble it off. So this term right here, and then this term right here, those get combined into some new function, f of r. Because if you notice now, these red things that I've bubbled off, they only are a function of r, okay? And so we could write a shorthand notation for our psi pz as literally z times some function in r, which is really cool, okay? And as it turns out, if we were to do psi star psi of pz, we would directly get the pz orbital, which is really cool. And I'm not going to show you my Mathematica graph. You can see that the picture of that is right here. Okay, so where this is my z-axis, and this is showing you that there, if we look at psi squared, of course, we're not necessarily going to get regions of positive and negative, but we label regions of positive and negative, and that will manifest later on as we get into bonding and molecular orbital theory. So we're going to do this in Mathematica. You're going to be able to just literally plot this equation, and it's going to be a p orbital. Really cool. A pz orbital. So how do we do px and py? Well, the situation gets a lot more complicated, okay? And it gets complicated because of our Heisenberg uncertainty in the x and y dimensions, okay? So remember that the commutator Lx, Ly equals I h bar Lz. Okay, so the fact that this has a value, right, that it's non-zero, that tells us there's uncertainty amongst the x and y dimensions. So we need a superposition to describe both px and py. So we need two separate superpositions, one for each orbital. And here's how we create that superposition, okay? So we're going to look at the psi21 plus 1, right, where ml equals plus 1, and the psi21 minus 1, here where ml equals minus 1. Okay, and if you follow through our nomenclature, right, that's R21, Y1 plus 1. And I'm going to, that's typically referred to as the P plus wave function, right? Check out the nomenclature. We're literally going to call all this stuff R21, Y1 plus 1, just P plus. Great, it's a wave function, okay? And when we have the psi21 minus 1, that's going to be the R21, Y1 minus 1, and that's going to make the P minus wave function. Okay, so each of these are their own wave functions that are suspect to Heisenberg. So we have to make a basis set of them. Okay? And again, that's because of the uncertainty that arises in the x and y dimensions. So our basis set becomes psi21 plus or minus 1. And the way that's going to go, this is the superposition we've created, where these ends, of course, are normalization constants. And we have the superposition of the P plus and the P minus state, which corresponds to ML plus or minus 1. Okay? So when we put that all together, right, we look up the R21 and the Y1 plus or minus 1. And so I'm just showing to you this as the plus or minus, right? So remember, when it's plus up here, that corresponds to minus there. And when it's minus down there, that corresponds to the plus right there. And then, of course, it's the same situation up here, okay? So what's pretty cool about all of this is if you kind of compare that we've got this z over a to the 5/2, we've got this 1 over pi to the 1/2, and if I back up and show you this, there's that z over a to the 5/2, and this other collection of constants, okay? With some algebraic manipulation, you can rearrange this equation to be, minus or plus 1 over the root 2, r sine theta, e plus or minus I phi, f of r. And that f of r is the same f of r from right here. And so I'm not going to go through the algebra to prove that, but if you rearrange these equations, you can get it so that f of r is the same as this f of r. And so hopefully you can kind of see where this is going. That's what creates the mathematical rationale for calling this either px or py. We still don't know which one is px or py because we have to apply our superposition. Okay? So moving on. So once again, we remember that psi21 plus 1 is p plus and psi21 minus 1 is p minus. And we have our general form of our basis set. So this, I'm not going to go through this derivation, right? We're just kind of showing you where it comes from. But by definition now, we can make a px wave function by the following superposition. So this is already normalized for you. So that's the normalization constant of the basis set. And that becomes a linear combination of p minus and p plus. And then now we also define the py wave function. So I'm going to remind you these are wave functions. Okay. Wave function. And so now we get this normalization constant, I over root 2. Totally fine that has an I in it because we're going to square it. Okay. And so it's also linear combination of p minus and p plus. And so now we're finally poised to define the px orbital as px star px, where px is this equation. Okay, so you have to square this whole thing so it becomes a quadratic. And then you have to square this whole thing to get py. And because we've now used this superposition, we've gotten around the uncertainty principle between the x and y dimension. And when we finish that off, what we end up with is, and more algebraic manipulation that I'm not going to go through, but we end up getting this function f of r, which are the same for all three orbitals, right? f of r for x is the same function of f of r for y, and it's the same function for f of r of z. But now with algebraic manipulation, okay, recall that my x in polar spherical coordinates is r sine theta cosine of phi, and y in polar spherical coordinates is r sine theta sine phi. And so that creates the px py orbital that we can see right here. Here's the results of the Mathematica simulation that you're going to do. And what's really cool is when you put all three of them together, we can see their x, y, z components, which is very cool. Okay. And also, even though these are the square, right? These are values squared. But because we have these imaginary numbers in these functions, we get negative regions, which is also kind of cool. Okay. And there's going to be physical significance to those negative regions. So I'll point out that, right, if you look at, there's the origin, and there's positive values, and there's negative values, right? So that's what gives us this plus minus region, okay? Because we have eyes in our situation. All right, so moving on. So